Hi kids, it's Mrs. Fravel. How are you today? Today is Wednesday, May 6th, and today we're going to talk about the second biogeochemical cycle in the ecology unit. You should have already done your water cycle assignments, so if you haven't, why not? Go do it. It's all due Sunday night, so is this. So without further ado, I'm going to talk about my favorite cycle, the carbon cycle. Okay, here we go. All right, let's go back a little bit. The carbon cycle. What is the carbon cycle? Carbon is a lot like water. Carbon cycles through the environment just like water does, with a few important differences. And we're going to talk about how that works and also how humans have kind of interfered with it a little bit. But first of all, what's carbon? So carbon is an atom. It has a molecular weight, molecular number of 6, and that indicates how many protons and electrons that it has. Carbon as an atom is pretty handy. It can bond with a lot of other atoms, and what happens is it does that and creates all of those wonderful, huge chain macromolecules that we talked about at the beginning of the year. Remember the macromolecules? Proteins, lipids, carbohydrates, nucleic acids. You remember. What those do is those come together to create tissues and cells, and the organisms that live here on Earth are referred to as carbon-based organisms because all of those macromolecules are based on carbon atoms. Okay? In the environment, in living things, carbon dioxide is used by plants for photosynthesis, and it is a waste product of aerobic respiration. It's what you exhale. Okay. All right. So what does carbon dioxide look like in the environment? Carbon in the environment, again, we mostly refer to it as being atmospheric carbon dioxide when it cycles through the environment. It is released into the atmosphere in a few different ways. First of all, it's released by respiration in animals, both on land and in the water. It's also released through geological activity. That means volcanoes. When a volcano explodes, which they do quite often on this tectonic planet, it releases carbon dioxide into the atmosphere. It's also released in combustion events naturally through wildfires and forest fires. And then it's also released in small amounts by decomposition of dead stuff. And we're going to talk more about dead stuff in the soil in a minute. Excuse me. The other half of that cycle is how is carbon dioxide absorbed from the atmosphere? Okay? It's absorbed by the ocean. The ocean and big lakes absorb tons and tons of carbon dioxide. It is also absorbed by plants when they do photosynthesis. Yay, plants! And then it is trapped underground through sedimentation when things die. So when organisms die, both plants and animals, they generally lay down quietly on the ground, and some of their tissues are decomposed by bacteria. That's how the flesh is eaten by bacteria. And some carbon dioxide is re-released into the atmosphere there, a very small amount. But most of the carbon in tissues, in dead things, is trapped and locked in the ground through sedimentation. Okay? However, humans have interrupted that natural cycle in a few ways, and it mostly has to do with what we do with that trapped carbon that is supposed to stay underground. That sedimentation of dead things, that's supposed to stay underground and be released very, very slowly. However, what we have done is we discovered, woo, if you take that fossil fuel material out of the ground, and that is called oil, coal, natural gas. If you take that out of the ground and light it on fire, oh mama, it burns. It burns like crazy. And a few hundred years ago, we discovered that we could use that material, oil, gas, coal, and natural gas, to power our society. So we invented combustion engines that burn fossil fuels as gasoline. And then if you have electricity in your house, which I'm assuming you do, when you turn on the lights that you see and the heat that comes out of your furnace, that is the product of burning coal and natural gas. And the electrons released by that burning of that carbon powers our lives. The byproduct of that is that it releases that carbon dioxide into the atmosphere in large quantities. When that carbon dioxide is released into the atmosphere, it stays in the atmosphere. It stays for a long, long time and accumulates, causing global warming. Okay? How does it do that? This is the greenhouse effect. So normally in that natural cycle, you guys, we have the best planet, right? Due to the presence of our atmosphere, which in this picture looks really thick, it is not this thick, but we have this wonderful atmosphere that traps just enough of the sun's heat to keep the water on our planet liquid and to keep a good temperature range for living proteins to not denature. So that is how our planet runs. However, when the atmosphere gets unbalanced by having too much carbon dioxide in it, that's like putting a blanket around the planet, and it just increases how much heat stays in the atmosphere and on the planet. And that increases global temperatures. And when you increase temperature, what happens to proteins? And what happens to living things? Excuse me. Okay. How do we know all of this is happening? How do we know that there is a problem with carbon dioxide in our atmosphere? Now, I'm going to pop back in. I wish we were in class, because what I'm going to talk about next is something that for some reason is rather controversial. I don't know. Just remember, everything that I'm about to talk about is based on valid science. And remember, science and hypotheses are data gathered by scientists that is rechecked and retested by other scientists. In order for a scientific concept to be considered valid, it has to be confirmed by other scientists. If it isn't accepted. Everything I'm going to talk about next has been verified and accepted by 97% of the scientific community who study climate. And that's a lot of people. Okay? So let's start. Okay. So how do we know that the carbon dioxide in the atmosphere is increasing, and why do we think that it is caused by humans? So here's where this all started. Back in the 1960s, they started measuring the amount of carbon dioxide in the atmosphere out in the middle of the Pacific Ocean. And that is actually measured and graphed every single day since 1960. This is called the Keeling curve, and I'm going to link today's Keeling curve data on the same page as this video, so you can go look at what the climate or what the carbon dioxide level was in the atmosphere today and yesterday. So when they started analyzing and graphing this data, they noticed that back in 1960, the concentration of carbon dioxide in the atmosphere was right around 300 to 320 parts per million. Over the years, as they have measured it, it has increased almost exponentially and logarithmically until today. The parts per million concentration of carbon dioxide in the atmosphere is over 400, and it's staying there, and it's just going up. Okay? All right, big deal. That's since 1960. That's what, 60 years ago? Who cares? That's not much. You can't prove anything with that. All right, let's stretch that out a little bit. So this data, this graph, is carbon dioxide, atmospheric carbon dioxide data taken from trees mostly. Trees can be pretty old, and you can analyze their tissues for how much carbon dioxide was in the atmosphere when they were building those tissues. And what scientists saw is that 1850, the year 1850 was when the Industrial Revolution started. You should know that from your history classes. That's when we started burning a lot of fossil fuels and dumping that carbon dioxide into the air with our factories and our engines. And since then, the level of carbon dioxide in the atmosphere has increased, again, exponentially until this is where we are today. So in the last, 170 something years, we've gone from 0 gigatons of carbon dioxide being pumped into the atmosphere to every year now we have over 8 gigatons pumped into the air. That's a lot. All right, big deal. That's only 170 years. They found more data. Scientists were able to take core samples from very old ice. The ice at our poles has been there since the last ice age, which is about 8,000 years ago. And in that ice is bubbles. And in those bubbles is the atmosphere from thousands of years ago. That's pretty cool. So they analyzed those bubbles. And what they saw is that from 8,000 years ago to 1,000 years ago, 1,000 years ago, not much change in the atmosphere, right? But then they analyzed 2 other younger cores, and the amount of carbon dioxide in the bubbles in that ice was significantly higher, okay? So this is from the year 2000 right here, this side. So this is the level of change, sorry, clicky finger. This is the level of change in carbon dioxide in the atmosphere. I gotta get out of the way, here we go. Just since the year 2000, mid 1900s. Okay? This red line right there, that red line is this graph and the Keeling curve, both compressed. Look at how different that slope is to the previous 8,000 years. Coincidence? Maybe. The Earth's climate has changed. The Earth has been around a long time and life has been on the planet for a long time. And the climate has changed many times. So maybe this is just another indication of natural climate change, right? People say that all the time. Sure. Let's see. Okay. This is another graph that they gathered data from mostly rock samples, which measures the carbon dioxide in the air from, 400,000 years ago, over 400,000 years ago. And they looked at how the atmospheric carbon dioxide really has fluctuated. It really has over the last 400,000 years. But it's stayed under 300 parts per million. It's never gone over there. And this spike right here, this spike here, and this spike here, they were caused by massive volcanic eruptions globally and or asteroid strikes. And those caused massive climate change, massive global warming, and then mass extinctions. Right here and right here, over half of life on Earth died. Okay? Here's where we are now. This was when humans started burning fossil fuels in our factories and cars. Is it a natural fluctuation? I don't think so. The data is suggesting that what we are doing now to the planet is going to possibly turn into what in the past has been pretty mass extinction events. And we are in the middle of a mass extinction event. Take my zoology class for more information on that. These spikes right here were all spikes in carbon dioxide, again, caused by asteroid strikes and or global geologic volcanic events. This trajectory here is only going to continue to go up unless we change what we're doing, and that's the struggle. That's the problem we're having right now, is how do we get this? How do we get this to come back down? That's up to us. We are the only ones that can change that. So for your assignment today, what I would like you to do is look at your carbon footprint. How do you as a person contribute to those curves and that exponential growth? And what are you willing to do to change it, to save it, to stop it, what's happening? There's another video linked on the assignment. Go watch that. And again, if you have questions, if you don't understand this, if you have doubts, if your mom and dad are mad that I told you all of this, please reach out to me. I'm happy to talk to anyone at any time about this. This is, as you might have been able to tell, a thing that I am passionate about. So go do your assignment, think about it and let me know what you think. Okay, don't forget to do the note guide and submit it with this and do your assignment. Okay, talk to you soon. Bye. Okay, get out of the way. Hold on.